This video is on section 7.6 notes, polar equations. So the next thing we're going to study that uses a lot of trig is polar equations. So when we talk about polar equations, we work in the polar coordinate system. And in the polar coordinate system, the pole is the origin. So the point 0, 0, we don't call 0, 0 anymore, or at least not the same way. And instead of calling it the origin, we call it the pole. The polar axis is the axis of the polar coordinate system. There's only one, and it's the positive x-axis. And then when we write polar coordinates, instead of being in terms of x and y, they're in terms of r and theta. So r is the directed distance from the pole to the point. You can think of it as like a radius, but you'll see that we have a positive radius if we measure it one way and a negative radius if we measure it another way, and I'll talk more about that in a second. And then theta is the angle whose initial side is the polar axis and whose terminal side contains the point. So here they kind of drew a picture. There's the polar axis or the positive x-axis. Here's the radius, that's how far the point is from the pole. And then theta is just that angle that the point makes with the pole. So here, if we have a point 2 pi fourths and we want to plot that point, then we actually kind of work backwards. Typically with rectangular coordinates, when we have x and y, we would find the x coordinate first, we would go right or left that amount, and then we would go up or down the y amount. When you're working with polar coordinates, you find the angle first, and then you do the radius. So for pi fourths, that's going to be right here. Pi fourths is right in the middle, and then a radius of 2. So I'm going to find pi fourths, I'm going to go to the pole, and I'm going to count a radius of 1, 2. And that is the point 2 pi fourths. And for this example, it says to write several other sets of polar coordinates because we know that when we have an angle in there, we also have coterminal angles. So whenever you write this point, there are infinitely many ways to write that coordinate using another number, but it would be an equivalent coordinate. So we have 2 pi fourths, but I can find angles that are coterminal to pi fourths. So for instance, I could take pi fourths and I could just add a full circle to it. So 9 pi fourths would be the exact same point because 9 pi fourths is coterminal. I could add 2 again, 17 pi fourths, that would give me the exact same point. I could subtract a full circle, so, oops, minus 2. 9 pi fourths minus, I don't feel like typing the fraction in again. There we go. Okay, so that gets me back to my original, and then I could subtract a full circle, negative 7 pi fourths. And then I could subtract a full circle again, negative 15 pi fourths. If I were to plot all of these points, they would just look like this. They would be in the exact same position. So a little formula to find alternative points would be r and then theta plus 2 pi k. Or if your angle had been in degrees, you could say plus 360k. Now there's another way to write these angles, and that's if the point uses a negative radius. So what I'm going to do is I'm going to mark the angle that is exactly halfway across the circle from this one. So it's exactly pi away from this one. That would be 5 pi fourths. And if we did a point using this angle, we would give it a negative radius, negative 2, 5 pi fourths. So if I was graphing this point, I would start at 5 pi fourths, and then I would do a radius of negative 2. So if you have a negative radius, instead of going towards the angle, you go away from the angle. So 5 pi fourths is right here. I would start at the pole, and instead of going towards 5 pi fourths, I would go away from it, 1, 2, and it gives me the exact same coordinate. And then from there, I could find angles that are coterminal to 5 pi fourths. So I would keep the negative radius, and then I would find anything that's coterminal with that, and that would give me another set of points that also work. So 13 pi fourths would work. 21 pi fourths would work. Negative 3 pi fourths would work. Negative 11 pi fourths would work. So if you take the radius and you switch the sign, then the first thing you need to do is go to the opposite side of the circle with your angle. So you're going to take theta, you're going to add pi to it to go to the opposite side of the circle. So adding pi to it goes to the opposite side of the circle, doing the negative of the radius kind of bounces it back to the correct side of the circle. It's like this is a double negative and they undo each other, is how you can think of it. And then plus 2 pi k would be us finding coterminal angles so that we can write other points. So all of these points that I wrote graph the same way. They all look exactly like this, but 2 comma pi fourths would probably be like the most simple version of it because everything's positive and the angle is between 0 and 2 pi. All right, so next example, we're just going to plot these polar coordinates, and we've got some that are in radians, one that's in degrees. So I'm going to go ahead and do some markings on here so that I know exactly where my angles are. So I've got pi fourths right here. Pi sixths is not down here. Pi thirds is not up here. Pi sixths is right here, and pi thirds is right here. So this is the 45, and then this is the 30, and this is the 60. Each of these little markings goes by 15. So pi fourths, pi halves, 3 pi fourths, this is 2 pi thirds, 5 pi sixths, there's pi, and then we've got 7 pi sixths, 5 pi fourths, 4 pi thirds, 3 pi halves, 5 pi thirds, 7 pi fourths, 11 pi over 6, and then 0 or 2 pi. It can be helpful to have at least one polar graph labeled so that you know exactly where those markings are, and to make sure that you don't accidentally label these. Okay, so 5 pi 6 with a radius of 2, I'm going to find 5 pi 6 and go to the pole, and then count out a radius of 1, 2. And I'm going to label that this is point A. There's point A. I'm going to find the angle pi. Here's pi. I'm going to count a radius of -3. So instead of counting 3 towards pi, I'm going to count 3 in the opposite direction. So 1, 2, 3. And I'm going to label this as B. So another way for them to write this exact point is they could have said a radius of +3 with a radian measure of 0. Or they could have said a radius of +3 with a radian measure of 2 pi. These would have worked as well. Next, we have a radian measure of negative pi halves. So negative pi halves is going down pi halves or counter, nope, that's clockwise, going clockwise pi halves. So down here, and then we're counting a radius 1 towards that. So here is point C. Point D is -1 and 450 degrees. So what I'm going to do real quick is just see what 450 degrees is coterminal with. That's 90 degrees. So -1 and 90 degrees. So now I'm going to find 90 degrees. 90 degrees is up here, and I'm going to count a radius of -1. So down 1. So point C and point D are actually the same. They're just two different ways of writing the same thing in radians and in degrees, using a positive radius, using a negative radius. All right, so next we're going to look at how to convert between polar and rectangular coordinates. So here I drew a right triangle. We have the radius labeled. We have our positive x-axis or the polar axis labeled. We have the y-axis labeled. Here's the angle theta, our x, our y. R and theta is up here, but you can also call this x and y. Because we also went right this amount and up this amount. So I'm not going to say that x is equivalent to r and y is equivalent to theta because they're measured using different units, but there is a way to write this point using x and y coordinates, just like there's a way to write this point using r and theta coordinates. So these are the conversions, and they'll look familiar because they're actually similar to what we did when we were talking through complex numbers. But they're just a little bit different because now we're talking about polar. So to convert from rectangular coordinates into polar coordinates, we just use the Pythagorean theorem here because the radius is the length of our hypotenuse for this triangle. So x squared plus y squared is r squared. That's how you're going to solve for your radius. And then to find the angle, you can just say tan theta. So here's your theta, right? This is the angle that you're talking about. Tan theta is opposite over adjacent, which is y divided by x. And so you'll be able to do that to find the theta for your r theta. Similar, if you go backwards and you want to find the rectangular coordinates from the polar coordinates, then to find cos, you would say adjacent over hypotenuse. I'll label this. Cos is adjacent over hypotenuse. And so to isolate the x, we would just multiply the r to the other side. X is r cos theta. And then sine is opposite over hypotenuse, y over r. And so to isolate the y, would just take the r and multiply it to the other side. And so here's how you could get just the x coordinate and just the y coordinate. And so these formulas are exactly the same as what we had been using for complex numbers, but now we're using them for polar and rectangular conversions, a different circumstance, but really the mathematics behind it is the same. All right, so we're going to go ahead and take this polar coordinate that's in terms of r and theta, and we're going to convert it into rectangular coordinates using x and y. So we're going to say x is r times cos theta, and y is r times sine theta. And anytime we see angles from the unit circle, we're going to go ahead and use exact measurements, just because it's better to use exact measurements rather than rounded decimals if we can. So 210, cos of 210 is negative root 3 over 2. That's 7 pi 6. And then sine of 210 is negative 1/2. So 6 divided by 2 is 3, so this is 3 times negative root 3. And then that's negative 3. And so if we were to convert this into rectangular coordinates, it'd be negative 3 root 3, comma, negative 3. So if we were to plot these 2 points, they would look identical. They'd be in exactly the same place. One is just in terms of polar, so it's in terms of angles and a radius. And then this one is in terms of left and right, up and down. That's the only difference. Okay, next we're going to convert to rectangular coordinates. And so for convert the rectangular coordinates to polar coordinates. So I'm going to use that Pythagorean theorem formula to find the radius. So I'm going to have x squared plus y squared equals the radius squared. So 9 plus 36, 45. And I'll go ahead and simplify that. I know that the radius is the square root of 45. I can simplify that radical rather than use a decimal. So this is the square root of 9 times the square root of 5. So 3 square root 5. And then for the angle, I have tan theta is y divided by x. And this is just -2. This is not a tangent value that is on the unit circle. A ratio of -2 does not show up on the unit circle for tangent, and so this is a calculator problem. I know that when I do tan inverse to solve for the angle, I only get answers that are in quadrants 1 or 4, and this point right here is left 3 up 6. Left 3 up 6 is a quadrant 2 point. So I'm going to need to take my answer and put that angle in quadrant 2 because it's not going to be there automatically. So here, if the problem doesn't specify, then you should be able to choose degrees or radians when you plug this into MyMathLab. If I give you an assessment, I should specify that for you. I'm going to go ahead and do degrees. So tan inverse of -2. This is a quadrant 4 angle. And so to make this a quadrant 2 angle, I'm going to add 180 degrees to it. So that's how we move tan into another quadrant. If it's in the incorrect quadrant, to find the second answer that you could get, you add 180 degrees. So 116.565 degrees in quadrant 2. And so this point would be a radius of 3 square root 5 and an angle of 116.565 degrees. All right. Next, we're going to look at graphing polar equations. And because we're learning all of this in one day, we don't have a lot of time to really truly learn how to graph polar equations. And so I'm going to show you guys how to graph them in your calculator. But I am going to point out some of the points and where you can see them on the graph. So first, we're going to go ahead and graph this in the calculator. We're going to hit the mode button. And function is how your graphs have typically been done already. You've been graphing just functions. That's how we always graph. So we're going to go down here to function, and we're going to go over to polar, P-O-L, and turn that on. And then when you go to y equals here to plug in your function, you're going to notice that instead of saying y equals, it says r equals. Because when we see polar equations, they are written as r equals instead of as y equals. So r equals 2 cos theta, 2 cos, and then here instead of, when I press this x button that I normally press, instead of giving me an x, it's going to give me a theta. Now, when you hit the window button, there's a few things we're going to adjust here so that we can see what's going on. So typically, when I have the theta, I usually do from 0 to 2 pi. Because that's going to give me the full circle. So 0 to 2 pi is typically going to get you everything you need to know, but there are a few exceptions, and I'll point them out when we get there. So 0 to 2 pi. Now, this theta step here is kind of an interesting one because it actually just changes how quickly the graph is created. Or how close the points are together. And if you have a bigger value here, then the graph is going to be created really fast. It's going to look like it's created with straight lines. It's almost going to look pixelated. And if you have a smaller value here, it's going to look a little bit better. So I'm going to put pi over 100. I usually try to do a fraction that's pretty small, not because I would literally want these little pieces to be pi over 100 big, but just because it makes it a nicer looking graph when I do graph it. So I'll show you guys the difference in a second. So we've got that. For x min and x max, it's just saying how big, because we know we're not graphing in terms of x and y, but this is just for the calculator, how far to the left and right, how far up and down do you want your little pieces of radius to be. So based on this, I can see that it goes to 2. I can see this goes up to root 2 and down to root 2. So I just decided to do -3 and 3. So left 3, right 3, down 3, up 3. That's what I'm going to do. And then since my thetas right here are in terms of radians, I'm going to hit the mode button and I'm going to actually put this in terms of radians as well. I'm going to make those match. So if I was graphing in degrees, then I should make this 0 and 360 and then maybe make the theta step like 1 or something. Okay, so I'm going to go ahead and graph this. And you can see it's a little bit squished because our screen is a little rectangular. It's not quite square, but you can see that it did graph this right here. I'm going to show you what happens. So I did pi over 100. If I did like pi over 4, I'm going to show you what happens here. It did not make a circle. So, and that's just because it's putting the points further apart, and so the graph is becoming pixelated. If I do like pi over 10, it gets a little bit better, but it's not quite as round. And you notice that it graphed it pretty fast. If I do pi over 100, it slows it down and it's nice and round. And then if you want it to go even slower, you can do like pi over, I wouldn't do 1,000, that might take forever to graph, but maybe pi over 200, hit graph. And if you press the enter button down here, you can actually pause it in the drawing. Which on this one doesn't really matter, but on some of the other ones, when it's like hard to tell what order things are graphed in, it will be helpful. Okay, so anyway, that's what the graph looks like. And you can see there's different points over here that are showing up on the graph. We should be able to look at these in the table. So here are your thetas. I would change these to be like 0, 30, 45. You might have to just plug them in and look at them individually. It'd be really hard to see these in terms of the radian measurements. If we redid this in degrees, we could go by 15 degrees. That's actually not bad practice. We're going to go ahead and do that. So go ahead and click the window button. We're going to change this to 0 and 360 degrees. And then I'm going to change this to graph 1 degree at a time. So I'm converting everything into degrees. I'm going to hit the mode button. And I'm going to put this into degrees. And then I'm going to graph. So it's giving me the exact same graph. It's just doing it in terms of degrees now instead of radians. Okay. And now if I look at my, because I did 1 degree at a time, still graphing. I can tell it's still graphing because there was something up there. Okay, so when I look at my table, it's giving me a theta of 1 degree at a time, and it's usually not very helpful to see 1 degree at a time. So if you want to see like every 15 degrees, like 30, 45, 60, you want to see something like that, you can go to table set right over here, which is in blue, and you can do the change in the table to be 15 degrees. And then go back and look at your table, and now it's going to show you the measures every 15 degrees. So it's giving them to me not in the exact values, but I can see here square root 3, here square root 2. 175 is not one we typically draw, 15 is not one we typically draw. So now I have all these that I can graph. And if we needed to see where those points came from, we can just plug in these unit circle values. So I can use 0 degrees. R of 0 degrees is 2 times cos of 0 degrees. Cos of 0 degrees is 1, so this is 2 times 1, which is 2. So at 0 degrees, we have a radius of 2. R of 30 degrees would be 2 times cos 30 degrees. Cos of 30 degrees is root 3 over 2. So 2 times root 3 over 2 is just root 3. That's like 1.7. So at 30 degrees, we go out to a radius of 1.7. 45 degrees. If I plug in 45, that would be 2 cos 45 degrees. which is 2 times root 2 over 2. That's just root 2, so 1.4. So at 45 degrees, we go out a radius of 1.4. R of 60 degrees. 2 cos 60 degrees would be 2 times 1/2. That's just 1. So at 60 degrees, we go out a radius of 1. And then R of 90 degrees is 2 cos 90. Cos of 90 is 0. So this would be 0, radius of 0. So at 90, we would have 0. And you can see that would be the top half of this circle, or scaled a little differently, scaled much bigger over here. So we can graph it by hand if we want to, but we probably don't. And if you needed to graph it and see specific points, this is how you could do it in your calculator. Okay, let's go ahead and turn to the next page and look at another graph. So this one says to sketch the graph of r equals 3 sine of 2 theta. So I'm just going to go over here, 3 sine 2 theta. For this one, I can see the radius of 3 is how far out this goes. I might want to make this window just a smidge bigger. I'm going to go out to 5 just to make sure I can see everything. Okay. So there's the first petal is what they call them, and then the second one is drawn over here, and then the third one is drawn over here, and then the fourth one is drawn over here. And the reason that they're not drawn first this one, then this one, then this one, then this one, has to do with positives and negatives. So this one has positive radius and positive degrees, and then you get some negative radius values, and so it forces you to push the petal on the opposite side of the circle. Anyway, it's interesting. It's something interesting to look at. But as you're graphing these, you can look at the table to get specific points to graph. And you can also remember, and here you can change the theta step. We can do like a 1 or a 2. And then as it's graphing, you can press enter to pause it if you wanted to know what order it was graphed in. So that's kind of a nice little trick there. All right, for this next one, we have this spiral. This is just r equals theta. And so it says theta is in radians, so I'm going to need to switch my graph into radians, and theta is just bigger than 0. So I'm going to go over here, I'm going to press theta. In my window, I'll do 0 to 2 pi, and I'll change the step to pi divided by 100. It looks like they go to -6, negative. I'll change this to -7. Okay, so hit graph. Oh, I forgot to change my mode. There we go, radians. Okay, now I hit graph. So there's my spiral starting. And my spiral didn't go as far, and you can see here's 2 pi, and this says 5 pi halves, which is bigger than 2 pi. This is one of those graphs where you're going to get more and more of the spiral as you add your coterminal angles. So if I want to see more of the spiral, I just have to go bigger than 2 pi. I have to go to like 3 pi, and I'll see a little bit more of the spiral. So 2 pi, and it's going to 3 pi. If I want to see even more of the spiral, I can make this bigger. And then I can change up here, 3 pi I can change to 4 pi. So here is 2 pi, there's 3 pi, there's 4 pi over here. So you just get to see more and more of the spiral if you make your window bigger. All right, Over here, these are the different formulas and what they look like when you graph them. So this would be helpful. When you look at these on MyMathLab, when you do these problems, these are going to be multiple choice problems typically for you, as opposed to like something you necessarily have to graph by hand. So you just need to be able to tell the difference. Here you can see these are both circles, but a cos is going to give you a circle that is along the x-axis, because cos is for x. Sine is going to give you a circle along the y-axis. So that's something that's kind of interesting. You'll notice this says cos 2 theta, and it gives you 4 petals. It gives you double the number of petals that you have. This is cos of 3 theta, and it gives you 3 petals. So if you have an odd number here, it's exactly the number of petals. If you have an even number here, then you double the number of petals. And I would say as you try these problems on MyMathLab, please don't rush through them or act like they're insignificant, because when you move on to calculus, if you choose to take a calculus course, in a calculus course, you do use graphs of these and you find the area inside of the petals. And so it's good to be somewhat familiar with these graphs. So take your time with them, play around with it, try different numbers, mess with it on your graphing calculator, make sure you really understand how it works on your graphing calculator so that when you get onto this in calculus, you would be able to work with these graphs. All right, what we're going to learn next is how to convert when we're working with equations. So I've just put these formulas at the top so that you can refer to them. First, we're going to look at equations that are in polar form and convert them into an equivalent rectangular form. And your goal whenever you're converting from polar into rectangular form is to find a recognizable rectangular equation, whether that be a circle or a straight line or something else. That's your goal. So with this first one, we have something that we can replace r cos theta with, but nothing that we can replace cos theta with. Similarly, over here, we can replace r squared with something that's in terms of x and y, but not just a plain r. And so what I'm going to do is I'm going to take this entire equation and I'm going to multiply it by r, the left side and the right side. So the left side is going to become r squared, the right side is going to become 2r cos theta. And then I can convert it into rectangular and get rid of all of the r's and all of the thetas. R squared is going to become x squared plus y squared. And r cos theta is going to become x. So this over here, the x squared plus y squared, should remind you of a circle. And then over here, the 2x just means that that circle has been shifted to the left or to the right. So what I'm going to do is I'm going to make it equal 0 by subtracting the 2x over. And so what I'm doing now is I'm making this equation into something that looks more recognizable. When I have a circle that's been shifted to the left or the right, we typically don't leave it in this form. We typically write it in the form so that we can see what the center of the circle is and so that we can see what the radius of the circle is. And that's a concept that's from Math 171. That might be from chapter 1. I can't remember what chapter, but it's definitely in Math 171. So if we look at this, we'd have x squared minus 2x, and I'm going to put a blank here so I can complete the square. We are reaching way back with this one. And then to do the completing the square process, I take this middle term and I divide it by 2. So negative 2 divided by 2 is negative 1. And then I take this number right here and I square it. Negative 1 squared is positive 1, and this is the number that completes the square right here. And then whatever I added to the left side of the equation, I also add to the right side of the equation. Right? So if I write this equation out, this would be x minus 1 squared, and then this would just be y squared. X minus 1 squared plus y squared equals 1. And so now I can recognize that this is a circle centered at 1, 0 with a radius of 1. And that's your goal, is to get the equation to something that you can recognize. So circle centered at 1, 0 with a radius of 1. All right, for this one here, we have r equals 4 is the equation. I don't have anything up here where I can take a plane r and replace it with an x or a y, and so I'm going to square both sides of the equation. So I'm just gonna, maybe not parentheses. Square both sides of the equation, squared, squared. There we go. R squared equals 16, and then the r squared I can take out and replace with x squared plus y squared. So here, this is also a circle, but this time the circle is centered at 0, 0 and has a radius of 4. So, and it might actually be good to write that. Centered at 1, 0 with a radius of 1. This is centered at 0, 0 with a radius of 4. So both of these are circles, and those are recognizable equations. All right, with this one, the sign on the bottom, I could just move to the other side. I could multiply it to the other side, and then r sine theta I can replace with y. So I'm going to go ahead and do that. I'm just going to multiply by sine, multiply by sine. So r sine theta equals 4, which is y equals 4. And this is a recognizable equation. Y equals 4 is just a horizontal line. So that one's good. I'll leave that one. And then here, theta equals pi fourths. For this one, to get rid of the theta, I don't have anything up here that says just theta is in terms of x and y, but I do have something that says tan theta is in terms of x and y. And so what I'm going to do is I'm going to tan each side, tan theta, tan pi fourths. And so tan theta is going to equal tan of pi fourths, and I know from the unit circle that tan of pi fourths is just 1. And then tan theta I can replace now with y divided by x. So I'm going to go ahead and do that. Y divided by x equals 1. And then typically when we're dealing with rectangular equations, unless we have something like this where it's a circle and the x and the y are supposed to be on the same side, typically we would get the y on one side and move the x to the other side. So I'm going to multiply by x, y equals x. So this is a linear equation with a slope of 1 and a y-intercept of 0. It's that perfect like diagonal line. So that's a recognizable equation as well. So that's your goal, is recognizable equations. Here, we're going to look at rectangular equations. We're going to write them into the equivalent polar equation. And our goal here is the same as well. We're actually looking for recognizable equations. And in this case, it's going to be helpful for us to have this sheet out so that we know what our recognizable equations are. Keep in mind that in these, your goal for most of these, pretty much all of them, is to get r completely by itself on the left side and have it in terms of theta on the right side. There's a couple exceptions to that. One exception is here if you have r squared equals this one. So this is one where you could have an r squared. And then another exception comes from this right here, when you have straight lines that go through the center of the graph, that go through the origin at 0, 0, or go through the pole, like y equals x. Those can be written as theta equals an angle measurement, because you would just find the angle pi fourths and then trace that line all the way through the pole, and that would make the line y equals x. So this is an exception to isolating r, and this is an exception. But otherwise, we would get the r alone on the left side, and we would have it in terms of theta on the right side. So I'm going to keep that in mind as I write these equations. All right, for this first one, y equals 3x minus 2. I'm going to take the y and replace it with r sine theta. And write the 3. I'm going to take the x and replace it with r cos theta. And then write the minus 2. And so since I want the r to be isolated on the left side, what I'm going to do is I'm going to take this term and just subtract it over to the left side. So I'm going to have r sine theta minus 3r cos theta equals negative 2 on the right side. And now what I'm going to go ahead and do, and this is going to be a strategy that you'll use on multiple problems, I'm going to take the r and I'm going to factor it out. So that way I have an r in two places, and that will make it so there's only one r. So factor out the r, and I get sine theta minus 3 cos theta. And then to get the r alone, I'm going to take this sine minus 3 cos and just divide it to the other side. So r equals negative 2 on the top, sine theta minus 3 cos theta on the bottom. And this isn't quite a recognizable equation. I can see that these equations are often in terms of sine and cos. I can see this right here, 4 over sine is pretty kind of typical. You might be able to look in the textbook, if you actually look at the textbook, and see that these are kind of typical equations. They just don't make these like special functions in here. But you can still see that if you compare it with these functions, the r is alone, it's in terms of sine and cos, it kind of makes sense. It looks like the rest of them. Okay, let's try this one right here. So we have x minus 2 squared plus y squared equals 4. And so I'm going to go ahead and simplify this a little bit because I have something for just x, but x minus 2 is a little complicated. The y squared looks like it could, instead of being this for y, I could use a y squared from this if I was able to get just an x squared. So instead of converting it straight into polar, I'm going to expand out this x minus 2 and see if I can get an x squared plus y squared in this problem. So I'm going to go ahead and write x minus 2 times x minus 2. And when I made these notes for you guys, what I tried to do is give you enough examples so that when you looked at the problems I assigned, you wouldn't see something that you hadn't seen before. So hopefully this is enough that when you try the problems on MyMathLab, you feel like you're doing something that you've already seen and not something where you just have to come up with the strategy out of thin air. There should be some recognizable strategies you can use. I'm foiling this, so x times x times negative 2, negative 2 times x, negative 2 times negative 2. So if I were to subtract the 4s, these would cancel each other out. Minus 4 and minus 4. If I tried to get them on the same side, they would just cancel each other. So here I'm going to write x squared plus y squared because I know that those can be substituted out together, and then minus 4x, and this is going to equal 0. So now I'm ready to make my substitutions. X squared plus y squared can be replaced with r squared. And then we have minus 4 times x, and the x can be replaced with r cos theta. So I'm going to say r squared minus 4 r cos theta. And then I'm going to do the same thing I did over here, where I'm going to try to isolate the r. So I'm going to factor out the r. So I have r and r squared, so I'll factor out the r, and that leaves an r behind, actually, from this first one. So what just happened is I basically factored out a GCF of r in this problem, and it's almost like I'm solving it by factoring. So I have two solutions for r, because this equals 0. I'm solving it by factoring. I have two solutions. I have this one, r equals 0. I'll come back to that one in a second. And then the other solution I have is r equals 4 cos theta. And 4 cos theta is a recognizable equation. That's this. So that's a good answer. R equals 4 cos theta is good. R equals 0 is literally just a point at the pole. R equals 0, if we were to graph it, would just be, you can see up here, this r equals 4 is like saying I'm going to follow the radius line of 4. I'm just going to follow it around the circle. It's a circle centered at 0, 0 with a radius of 4. So if it was r equals 0, I would just find a radius of 0 and I put a dot there. So this r equals 0 is literally just a dot at the pole. This isn't really anything, but this is the graph that we would have. So this is our recognizable polar equation. This is what we end up with. This is just one dot. All right, let's go ahead and try this one. X squared plus y squared equals 9. Well, I know that x squared plus y squared is just r squared. R squared equals 9. And then when we have these recognizable equations, we don't want to have r squared unless we have this one. This is the only one with r squared, and we don't have that situation happening here. So since I don't want to leave this as r squared, I'm going to go ahead and square root each side. So this is r equals 3. A circle, I'm just going to trace the radius of 3, trace that around the circle. That would be a circle centered at 0, 0 with a radius of 3. So r equals 3 for that one. All right, for this one, I could replace y with r sine theta. I could replace x with r cos theta, but this one is a little bit easier if instead of doing those separately, if I just look at what would happen if I do y divided by x. And you'd get there if you did it the other way, but this way is going to be a little faster. So I'm going to divide by x, and that's going to give me y divided by x equals -1. And so what I'm going to get for y divided by x is tan theta. If you did it the other way, you would end up with a sine over cos, and you'd have to replace that with tan theta. So this way is a little bit easier. And then here we either have to have r equals something to write an equation, or this is the one situation where, like this one, we can have theta equals an angle measurement. And so that's the one I'm going to do here. So I'm going to do tan inverse of -1 so I can figure out what that angle measurement is. So where on the unit circle do you have a y coordinate divided by an x coordinate that gives you -1? And that happens at 3 pi fourths. It also happens at 7 pi fourths. So you could say theta is 3 pi fourths. You could say theta is 7 pi fourths, or you could use any angles that are coterminal with that. Any of those angles would have worked as well. Okay, so between all of these examples, anything that you should have to convert should be like one of these. If it's not, go ahead and send me an email and ask me for help, and I'll make sure that I give you some hints on how to work with any of those problems.